Am I audible? Welcome, dear friends. Am I audible? Okay, thank you. The plan is to discuss the important working fluid properties, namely ideal gases. So we would be looking into the entropy change expressions for ideal gases, as also you would be applying the first law of thermodynamics to the systems involving ideal gases. Ideal gases and steam. These two are important working fluids in practical energy conversion equipments. For example, in engines, uh, you know that IC engines, for example, internal combustion engines, be it a petrol engine or diesel engine, you can visualize them as the working fluid. We can visualize the working fluid as being closer to the gas form. Okay, though you have fuel injected in petrol engine and you have diesel injected in the diesel engine, or there is gas engine. So a good assumption for analysis would be that we can assume the working fluid. Working fluid means the fluid which participates in the energy conversion process to behave as a gas. And in idealized scenario, we can assume that that fluid is behaving as an ideal gas. Okay, so ideal gases you have been introduced to in physics, right? So I won't be revising those very basic terms like PV is equal to nRT and all those stuff. Okay, so I will assume that you know those gas equations, you know Boyle's law, Charles law, you know Gay-Lussac's law. Okay, all this I would be assuming. My purpose would be to apply the first law of thermodynamics and get the expressions for work transfer, heat transfer, and entropy change. Okay, so that would be the objective, and we would be considering various processes in that case. So we would be considering constant pressure process, constant volume process, and I would like to relate it to the real world also. When we discuss those processes, I would be giving you examples of real world so that you would appreciate the need for such a theory. Okay, so a very simple question has been asked on the poll, and this has to do with your understanding of a pressure volume diagram. Okay, and the understanding of the process, which is a constant pressure process. And interestingly, I find that very few students have answered the question correctly. Okay, very few students have answered the questions correctly. Negligible number of, not negligible, but maximum number of the students have answered the question wrong. Okay, they have got the answer wrong. Okay, and I would be showing you how it is wrong. Okay, so what is asked is how would a pressure volume diagram look like? Okay, when you consider a constant pressure process involving ideal gas as a working fluid. Okay, so let me shut down this poll. There are 55% of the students have answered the poll. I assume that others are also answering, but I would not wait for them to respond. Okay, and I would show you the results of what the students are saying about this. Okay, so if you see the result, you see that about 44% of the students feel that a constant pressure process is a curve. Is a curve. Okay, and let us see what is how it looks like, and I will be drawing the constant pressure process. Let me shut down this result. As you see that around 70% of the class, around 70% of the class has, those who have voted, they have voted incorrectly. Okay, so let me show you what I mean and what I will be discussing. Okay, so if you now tell me whether the whiteboard is seen or no. I don't feel it is seen. Let me share the board first. Sorry, let me share the board. Okay, so can you see the whiteboard? Are you able to see the whiteboard? Pawan is saying no. Okay, wait. Let me retry. Now, can you see the whiteboard? Okay, thank you, Sushant. Thank you, all of you. Look at this. Okay, what was the question asked? The question was about the representation. Okay, so let me represent this constant pressure process. Okay, what is happening? Okay, so we are talking about ideal gas as a working fluid now. All my discussions would be now on ideal gas as a working fluid, and we are talking about certain process which is a constant pressure process. Okay, so process, you know that it means that, let us say I am taking a piston cylinder arrangement. Let us say I am taking a piston cylinder arrangement. Okay, and this, and let us say that I am talking about an expansion process, and assume that this piston cylinder arrangement, uh, this is a piston cylinder arrangement, and let us say that there is an expansion process. Okay, there is an expansion process. So and let us say that the pressure is, this expansion is happening at constant pressure. Okay, at constant pressure, it means what? It means that, let us say that system moves from a state 1 to a new state. Okay, when it's an expansion process, obviously you will have V2 greater than V1, because it is an expansion process. So when there is an expansion process, the V2 would be greater than V1. And when you are talking about a constant pressure process, pressure is constant. This obviously would mean that P1, that is the initial state pressure, would be equal to final state pressure. Okay, so if I want to represent this, obviously let us say that initially the volume was V1, and now the volume is V2. Initially the pressure was P1, and now the pressure is P2. So look at this. This is the state 1, which is having the pressure P1 and volume V1, and the state 2, which is having the same pressure, the pressure P2, but the volume has now increased to V2. So the volume is now V2. So this is the state 2. So look at this process. If you join this two states, okay, so this is a horizontal line. Are you getting this? So it means that the pressure volume diagram, right? A pressure volume diagram for a constant pressure process, obviously has to be a horizontal line. Okay, so I hope that you are now very clear on how to relate the processes which are happening in the actual life, okay, with the representation on the different diagrams. Okay, so you need to think on this, that what is happening, okay, during this. So let me just to check whether you have understood this or not, let me just ask you another question, very simple question. So let us see whether you understood or not. Okay, So again, there are very interesting answers, and uh, this why students are making such a mistake, I don't understand. And though majority of the students are answering it correctly, but still there is a sizable number of students who are not appreciating this very simple concept. Okay, either they are not attentive or they are not following anything. So again, let me close this poll and let me show you the result. Okay, so you see that again 60% of the class has answered this correctly. The correct answer is obviously, if you think on it, that the volume, initial volume V1, if it has to be equal to the final volume V2, okay, final volume V2, and then if you are talking about a process, let us say if you are talking about a compression process at a constant volume, then you would find that if you are increasing the pressure at constant volume, then you would find that it would be a vertical line. It would be a vertical line. Okay. So any process which is to be represented on a pressure volume diagram with the volume remaining constant, obviously it would be a vertical line. Okay. So let us not discuss this much now. I want to go to the application of, so I would be concentrating my attention on this first process, that is constant pressure process, and then we would, if time permits, I would go to the other types of processes, but you need to link, okay, you need to link what is happening, okay, in the physical world, and you need to be in a position to abstract the things and represent those processes on the different diagrams like pressure volume diagram, temperature entropy diagram, and so on. Okay, so today I would be restricting my discussion initially at least to a constant pressure process. So I had drawn, let me hide this and show you the board. Okay, I hope the board is seen now. Yes, Kamlesh, is it seen? Are you able to see the board, whiteboard? Okay, thank you, all of you. Let me first discuss now the diagram which I had drawn here. Okay, so let me ask you this diagram, which is a piston cylinder arrangement. Let me ask you whether this is a closed system or open system. Tell me this answer in your question column. Whether this is a closed system, the diagram which I had drawn here, okay, or it is an open system, and why? Whether this is a closed system, Vedant is saying something. Okay, closed. He is saying closed. Whether it is a closed system and or open system, and why? Okay. Okay, Atharva is saying it is closed. Sushant is saying it is closed. Okay, all right. Darshan, Neha, Sushant, Yeshraj, everybody is saying that it is closed. Nobody is saying it is open. Kamlesh is saying closed. Yugandhara is saying closed. Neha, Vedant, Atharva, Abhijit. Okay, all right. So it is a closed system. Why it is a closed system? Because no. Energy bahar nahi jati hai. Gargi, it is wrong. The answer is correct, but the reason is not that. The reason is, Gargi, that it is a closed system because there is no mass transfer. Okay, there is no mass transfer. There is an energy transfer, but there is no mass transfer. Okay, so let us look at it now. Let us try to apply. Okay, let us try to apply. So it is a closed system. Which I had drawn is a closed system. Okay, so now let us try to apply the first law of thermodynamics to it. So write the mathematical expression for first law of thermodynamics. Let us say I will draw one process. Now let me redraw this. We are talking about a process 1 to 2, and I am talking about a constant pressure process, and I am showing now, let us say, heat transfer to it. Okay, so let us say there is an ideal gas in this piston cylinder arrangement. Let us say that there is an ideal gas in the piston cylinder arrangement. Okay, and let us say that there is a transfer of heat from from the surrounding to the system. There is a transfer of heat from the surrounding to the system. Okay, right? So what would happen? Okay, my question is, what would happen to what would happen to let us say internal energy, okay, and what would happen to work? So what would be the direction of work transfer, and what would be the what would be the internal energy, whether the internal energy would decrease or increase, and what would be the work transfer? Are you getting the question? We are talking about a piston cylinder arrangement. Okay, let us say that I had drawn is a state 1. Okay, state 1. This is state 1, and then the system moves to another state. Or let me redraw this. I'll just show it on the same diagram. A new state, I would just show it by a dotted line. Okay. So let us say this dotted line would represent the final position of the piston. Final position of piston. Okay. So I want you to tell me what would happen to the, whether I'm saying work would increase is not the correct word. Work increases, work decreases is not the way we talk about work. Vedant, are you getting my point? When you are talking about work transfer from the system to the surrounding, or to the system, or from the surrounding to the system. Okay, this is the way we talk about work. We don't talk about whether work is increasing in the system or decreasing in the system, because work and heat both are boundary phenomena. Please note, work and heat both are boundary phenomena. So we don't say that there is some work into the system like this. Okay. So otherwise saying that the work would be transferred from the system to the surrounding. Okay. And anybody else is saying something? Kamalesh is saying there is no exchange along the boundary, but nobody is answering earlier question. So can you calculate what would be, how do we calculate the work transfer in this case? How do we calculate the work transfer in this case? Okay, and can we show that work transfer on a pressure volume diagram? On a pressure volume diagram. This is the questions I will be asking you. So why is that? Because it is a closed system. Because it is a closed system. Okay, so the work transfer during the process 1 to 2 is obtained by integration of P dV from 1 to 2. Okay, so if you want to find the work transfer from 1 to 2, then we need to integrate from 1 to 2 P dV. Okay, is this clear? Right? So if you integrate, what you will get? P dV. This is a constant pressure process. So I can take P outside the integral, and this would be integral of dV from 1 to 2, because P is constant. So what you will get is, it is P into V2 minus V1. V2 minus V1. Are you getting this point? P is equal to V2 minus V1. If you apply the gas law, which says that P1 V1 is equal to MR T1 and P2 V2 is equal to MR T2. So for ideal gas, this expression of work transfer, can be written as, obviously, MR T2 minus T1. Okay, so this, whatever I am writing on the board here, that is the expression W12 is the expression for work transfer when you are considering a closed system. Like what I had shown here, a piston cylinder arrangement, and that expression for work transfer is given by either P into V2 minus V1 or P or is equal to mr T2 minus T1. It's same thing. It is same thing. What about the change in internal energy? How do you calculate the change in internal energy? Okay, before that, what is the meaning of this? W is equal to integral of PdV on a pressure volume is like this. What is the meaning is like this? Suppose this is your dV, small dV. Okay, so this small dV, if this is small dV and this is your total is P. Okay, so this area is dW. dW is equal to PdV work. Okay, for an elemental change during a process. But if you want to consider the entire process from V1 to V2, entire process from V1 to this is V2. Okay, entire process from V1 to V2, then this entire area, this whole area which is under the process 1 to 2 on a pressure volume diagram, represents the work transfer. So this is the transfer of work. If it is an expansion work, this transfer would be from the system to the surrounding, and if it is a compression work, then it would be from the surrounding to the system. Okay, so what I had drawn here is the expansion work. That is, the work transfer is given by P. This is P, which is P1 into P2 upon into V2 minus V1. So this is del P. This is the area of a rectangle on a pressure volume diagram. So area of a rectangle on a pressure volume diagram, okay, that is the area under the curve 1 to 2 would represent the work transfer during constant pressure process. If you are considering a closed system. Okay, closed system. What about the heat transfer now? What about the heat transfer? So the heat transfer, if you want to find the heat transfer, apply the first law of thermodynamics. To this process 1 to 2. So what is the mathematical statement of first law of thermodynamics as applied to the closed system? The mathematical statement of first law as applied to the closed system is Q is equal to delta U plus W. Delta U plus W. This is nothing but delta U plus P delta V, or we can just write delta PV. Okay, it's same thing. So this, you all know that U plus PV by definition of enthalpy, U plus PV is equal to H. So Q is equal to this delta U plus delta PV means delta of U plus PV, which is nothing but delta H. And you know that from the definition of specific heat, so delta H is, so I will write over here. So Q is equal to delta H, or it is mCp from the definition of specific heat at constant pressure, T2 minus T1. Okay, so the expression for heat transfer, during the constant pressure process, and here we are considering a constant pressure process undergone by a closed system, it is given by Q is equal to mCp T2 minus T1. Now let us find the entropy change then. If it is so, what would be the entropy change now? So the entropy change during the process 1 to 2 is equal to integral of del Q by T. Okay, which is equal to integral of mCp dt by T. mCp. I hope you are appreciating this fact. Okay, which is equal to mCp log to the base E T2 by T1. Okay, so what I have done is the following. Let me use some other pen here. Okay, so this expression is what? This expression is the expression for entropy change of the gas, as it expands from 1 to 2, Okay, this expression which I have written here, this expression is the expression of the gas work transfer from the system to the surrounding when it expands from the volume V1 to volume V2 at constant pressure. Okay, for a closed system, This is another expression for the same. This is another expression for the same. Okay, and this expression, that is Q is equal to delta H, that is mCp T2 minus T1, is the expression for the heat transfer. So this would be the heat transfer. Okay, mCp T2 minus T1. Okay, T1, and this would be the work transfer. That would be what? That would be P V2 minus V1. What would be the change in internal energy? Change in internal energy would be, it is always change in internal energy by the definition of specific heat at constant volume. Change in internal energy would always be mCv T2 minus T1. Okay. And change in entropy during this process, what would happen to the entropy? Whether it would increase or decrease? What would happen to the entropy? Whether it would increase or decrease? There is a heat, and if you draw the entropy diagram of expansion, you would have this kind of curve. Okay, so this will be more clear to you as we saw numerical. So before solving one numerical, let me ask you one poll question, and maybe whether I have got that question or not. Let me check. Okay, yeah. All right, I'm launching this poll question, and then I will be solving one numerical on this. So let us solve this. Let us write this. For a closed system, which I discussed now, the expression for work transfer. Okay. it is interesting that I have already explained you this with such a slower pace. Okay, and there are some students who are still answering it incorrectly. Okay, what I have explained you now is a closed system case. I had considered an ideal gas air enclosed in a piston cylinder arrangement, and I had shown you that the work transfer is P into V2 minus V1. Okay, work transfer is P into V2 minus V1, and I had also shown you that by applying the gas equation, general gas equation, P1 V1 is equal to Mr T1, and P2 V2 is equal to Mr T2. It is also equal to Mr into T2 minus T1. Okay, so the correct answer is uh, those who have voted it. The correct answer is the both 2 and 3. That is the correct answer. Both 2 and 3. Okay, so I am closing this poll, and now I will be solving this one numerical so that you would understand this more clearly. Okay. This case you would understand more clearly. So that is the objective. So let me take one numerical on this, which is a university numerical, okay, which was asked for about 6 marks in some exam. Right. So I will erase this, and I will be solving. I will be taking the question. Okay. So let me share the result first. The result is the answer is for a closed system, the work transfer is given by both the expression, that is Mr T2 minus T1 or P into delta V, P into delta V. Okay. I'm hiding this, and you done this question. I'm detecting it, and you can also copy it down from the board. Okay. So the this is a problem with the closed system. The numerical is a closed system. So consider a closed system. Consider a closed system, and let us say that the pressure remains constant. Pressure is constant during expansion. Pressure is constant during expansion from is constant and is equal to 105 kilopascals. As the gas expands, as ideal gas expands from some volume V1, initial volume expands from a volume of 0.25 meter cube to a volume which is 0.45 meter cubic meters. Okay, and let us say that in the heat transfer, the temperature changes. Okay. Can you see the board now? Are you able to see the board, whiteboard? Are you able to see the whiteboard? I'm asking them, not replying. Let me ask them again. Are you able to see the whiteboard? Waiting for next screen, audience view. No one can see this here. Okay, let me retry this. Okay, all right. Now we are seeing this. So what I written is the we are talking about the closed system, the pressure is constant, which is equal to 1.5 kilopascals, and we are considering an expansion of the gas from 0.25 meter to 0.5 meter cube, and the temperature increases. The temperature increases from 283 Kelvin 283 Kelvin to a higher temperature, which is 513 Kelvin. Okay, so you need to calculate. You need to calculate the heat transfer during the process 1 to 2. You need to calculate the work transfer in process 1 to 2. You need to calculate the change in internal energy during so some of the answers in the questions column. Because it is a constant pressure process. Okay, so I can put this process on a pressure volume diagram. Let us say the process is from 1 to 2, because you see that the expansion process V1 is equal to 0.25 and V2 is equal to 0.45, and this pressure V1 is equal to P2 is equal to 105 kilopascals. So the work transfer, for example, would be so this area is the work transfer. Okay, this is work transfer. That obviously is into V2 minus V1 into V2 minus V1. So 105 kilopascals means kilonewtons per meter square. Okay, into V2, that is 0.45. Solve this, it would be how much? How much is the value for work transfer? You find out and tell me. Similarly, heat transfer is 3 minus 283. Okay, so we'll assume that there is some other gas whose Cp is 0.44, and that will give us some answer, right? Similarly, U12 would be you need to apply the first law of thermodynamics for finding U12. Okay, you know that U12 is equal to delta U plus W12. So delta U would be calculated as Q12 minus W12. So that would give us the delta U answer. Okay, and the change in entropy, del S is integral of del Q by T, which is mCp log to the base C T2 by T1. So you already know what is T2. It is 513, and T1 it is 283, and Cp is given as this is some other gas whose Cp is 0.44 and M is 1 kg. Okay, so this would give us some answer, right? So tell me these answers now. What are answers you get for heat transfer, work transfer, change in internal energy, and change in entropy? Okay, calculate and tell me the answers. Calculate and tell me the answers. Okay. Anybody who has got the answer? Neha has got, yes, Neha, it is correct. Neha, you are right. Kunal and Neha are getting it correct. Anybody from your side? It's pretty simple actually. If you have got the concept right, it is simply a matter of substituting the values in very simple expressions and getting the answer. What you must know is what expressions you should use. Okay, and you should appreciate what is happening physically also. Why the entropy would increase, what would be the direction of work transfer. The meaning of, for example, when you are getting W is equal to 21 kilojoules, the meaning is when you are adding certain heat, okay, that would lead to the expansion work, which is a positive work. That is, for the expansion work, you know, is the work done by the system on the surroundings. That is why you are getting the value as 21 kilojoules, and you are supplying 101.2 kilojoules of heat. So what happens to that heat? So partially that heat which is being supplied to the closed system, okay, that heat partially goes for expansion work, and partially it would increase the internal energy of the gas. Okay, so the gas would get heated up, and also the gas would expand. Okay, so there are two results. Okay, there are two outcomes of the heat transfer. So when you are transferring a heat of about 101.2 kilojoules, okay, of that 101.2 kilojoules, you are getting about 21 kilojoules as shaft work, as expansion work, and the remaining heat, where it does not disappear, where does that heat go? That heat goes in increasing the internal energy of the gas. What happens to the entropy? You also tell me the value of entropy change. Okay. So tell me the other values, Kunal. Can you tell? Change in internal energy and entropy change. Okay, you can solve this at home. I will just at home, obviously. You can solve it afterwards. So before I close down, I'll just touch upon what is the open system expression for this. Then I will stop this. Okay, entropy change otherwise getting 0.267 otherwise. Okay. Solve it, but everything is written on the board is matter. It is just remember that it is locked to the base key and not locked to the base. So just click the answer of otherwise is getting as 0.267. Where the other getting is as the same value and entropy change. Whether it is 0.7 which otherwise gone. Okay. All right. Thank you very much. Thanks for being online. In the next class, we would be discussing some other interesting processes. You know that we talked about only one process, which is a constant pressure process, which I had shown you as an example in a piston cylinder arrangement. It was a closed system case. You would encounter a open system case also where the pressure is constant, but the volume is increasing when the heat is being transferred. Then there would be some constant volume processes, both the open system case and closed system case. There would be isothermal processes where the temperature remains constant. Then there is a reversible adiabatic process, where the heat transfer is zero and the entropy also remains constant. So all this is considering, and we would be applying the first law of thermodynamics. We would be finding out what is the expressions for work transfer, heat transfer, change in internal energy, change in entropy for all such cases. Okay, because these are very important cases, very relevant cases in if you want to actually analyze the engines which involve the gases. For example, gas turbine power plant. Okay, gas turbine power plant is a power plant where you'll find that uh, gases are used as working fluid. Okay, there you encounter such processes. Your internal combustion engines is another example where you would find gases expanding during a power stroke, okay, of the engine. All this would make sense, and when you analyze the actual engines, analyze the plants, turbines, these expressions would become very handy for you. Okay, so in higher studies, if you go for higher studies, these expressions would be used for modeling the mathematical modeling of that system. So thank you. I hope you understood this. Thanks a lot for being online. Have a good day. Thank you.